Imagine a hidden reservoir beneath our feet, holding more carbon than all the plants on Earth and 3 times what's in our atmosphere. This vast storehouse is the soil, and for centuries our farming practices have been depleting it, releasing ancient carbon back into the air. But what if we could reverse that trend? Could changing how we farm actually pull enough carbon out of the atmosphere to slow climate change? Or is soil carbon sequestration too good to be true? Everything is a system. For grade 11 students, understanding complex interactions is key, and few systems are as vital and intricate as the carbon cycle beneath their feet. Today, we'll explore how agricultural management practices impact this critical system and whether they can help store carbon and combat climate change. Dr. Anya Sharma, a leading soil biogeochemist at the University of California, Davis, explains it like this. Plants are nature's carbon capture technology. Through photosynthesis, they pull atmospheric carbon dioxide and convert it into organic carbon, allocating a significant portion below ground through roots and exudates. Once there, billions of soil microbes get to work. These microscopic organisms can either stabilize that carbon into long-lasting soil organic matter, locking it away, or they can respire it back into the atmosphere as CO2, depending on the conditions. Understanding this dynamic is crucial for managing our planet's largest terrestrial carbon reservoir. In our soil carbon system, we track 6 key components. Our primary external input is agricultural management practice, like what farmers choose to do. This influences internal output such as the plant carbon fixation rate, soil microbial activity, soil organic carbon stock, and the soil respiration rate. All of these ultimately determine the net soil carbon balance, which tells us if soil is storing or releasing carbon. Let's trace these relationships. First, agricultural management practices have a positive relationship with plant carbon fixation rate. Regenerative farming, like cover cropping, keeps plants photosynthesizing longer. A higher plant carbon fixation rate then has a positive relationship with soil microbial activity, as more plant carbon feeds the microbes. Soil microbial activity has a complex dual relationship with soil organic carbon stock. Microbes can stabilize carbon into long-term storage, but they also respire some away. Critically, external factors like rising temperatures have a positive relationship with soil respiration rate, meaning warmer soils release more CO2. Finally, soil respiration rate has a negative relationship with net soil carbon balance. If respiration outpaces carbon inputs, the soil becomes a source of carbon, not a sink, accelerating climate change. Build your soil carbon model to explore these critical dynamics. What if we dramatically shift to regenerative agriculture globally? Could we really pull enough carbon out of the atmosphere to slow climate change? Or are the biological limits of soil carbon sequestration too great? Understanding soil carbon dynamics opens doors to impactful careers. Soil scientists study the physical, chemical, and biological properties of soils, earning between $65,000 and $120,000 a year. You could also become a carbon market analyst, verifying and trading agricultural carbon credits at environmental finance firms, with salaries ranging from $80,000 to $160,000 annually. Everything is a system. Model it, build it, simulate it, understand it. Visit ModelIt K12.com.